Okay. Hello dear students, hope you all are fine. In the last class, we discussed the three special formula of integrations. Today, I give you proof of one of them and rest two will be your homework. Let us remember that three formula. Number 1, integration of under root of x square plus a square dx is equals to x by 2 under root of x square plus a square plus a square by 2 log of mod x plus under root of x square plus a square and plus c. This was the first one. And the second one was, that is number 2, integration of x square minus of a square dx is equals to x by 2 under root of x square plus x square minus a square, and here minus a square by 2 log of mod x plus under root of x square plus a square plus c. And the third one is number 3, that is integration of under root of a square minus x square dx is equals to x square by 2 under root of a square minus x square and plus a square by 2 sin inverse of x by a plus c. These were the three formulas that we have discussed in the last class. Today I give you proof of one of them, and let us do the integration of root under x square plus a square, and these two, number 2 and 3, you try in the same way as your homework. Let us see. We have I equal to integration of under root x square plus a square. We apply the integration by parts method. Here this one will be taken as your first function and 1, here we take 1 as the second function. So, as per integration by parts, integrating by parts, we get, that is I equal to first function, that is root under x square plus a square, integration of second, that means this is dx minus integration derivative of root under x square plus a square and integration of dx whole close and dx is here. So, this is equals to, the integration of dx is x. So, we have x root under x square plus a square minus, that is integration, and here what we can write, the derivative of this one. So, we know that the derivative of x square plus a square, that means it can be written as 1 by 2 upon x square plus a square, and for this x square you will get 2x here, and for this x you will get, for this integration of dx you will get x again here and dx will be here. So, finally, x root under x square plus a square minus these two will cancel out and this x and this x become x square. So, you will have x square upon root under x square plus a square dx. So, now look here, this part the integration is over, but this part we need the some adjustment to do the integration over this one. So, what we can do? We just make an adjustment by taking plus a and minus a in the numerator. So, what we can do? See, x root under x square plus a square minus integration, that is x square plus a square I am taking and minus a square I am taking in the numerator, and that is x square plus a square and dx. So, from here I can make this integrand as that is equal to x root under x square plus a square minus this is x square plus a square by that is x square plus a square not in root, that is under root of x square plus a square, and this minus and this minus become plus, that is a square integration of dx upon root under x square plus a square. So, ultimately x under root of x square plus a square is minus, see look here, that is x square plus a square in the numerator, and in the denominator within the root we have root under x square plus a square. That means same thing in the numerator as well in denominator. So, if we are dividing it, you must get integration of root under x square plus a square, and here that is a square, that is integration of dx upon root under x square plus a square. Now, look here, this is exactly the same thing of I only. That means this what can be replaced by I. So, we have I here in the left hand side, and here once again we have minus I. So, this minus I we can take to the left hand side, and that will become 2I, and 2I is equals to x root under x square plus a square, and that is plus a square, and the integration of this by using our special form, special 6 forms, integration of this is given by log of mod x plus under root of x square plus a square and plus c, you can put c here also. So, now this I is equals to what, x by 2 root under x square plus a square by 2 log of mod x plus root under x square plus a square and plus c. So, this is the final result, or this is the proof of this result, that is I equal to x by 2 under root of x square plus a square by 2 log of this one. So, here look here, so integration of root under x square plus a square dx is given by this x by 2 root under x square plus a square by 2 log of mod x plus root under x square plus a square plus c. This way you can do other two problems, both of them will be solved, or you can find that result by using integration by part method. Okay, dear students, I think now it is clear, and with this we have completed almost all the special forms of the integration. Now we can do some 1 or 2 questions over this special rules. Let us see the problem. Now look at this problem, that is integration of cos x under root of 4 plus sin square x dx. Okay. Now this we can simply solve by substitution method. Let us put this sin x as t, putting this t is equals to sin of x. That means your dt is what? It is cos x and dx. Therefore, your I will change as, that is integration of cos x dx can be written as dt, and this under root of 4 plus t square. Now, this one can be written as 4, that means you can write 2 square plus t square. Now, exactly the same form which we have proved. That means under root of a square plus b square or a square plus x square. Okay. So, that form we can use directly here, and that is what? That is t by 2 under root of, that is a square that is 2 square plus x square plus a square by 2. A square by 2 means what? A square by 2 log of mod t plus root under t square plus a square. A square means what here? A square is your 2 square and plus c. So, this will give you t is what? T we have assumed as sin x, so it will be sin x by 2 root under 4 plus sin square x, and plus, that is 2 will cancel. So, that means 2 log of sin x plus sin square x plus 4 plus c. So, that is the integration of this one, root under t plus, by using this one, by using this special 3 forms. Okay. Now, these problems we have used here the substitution method. Okay. Now, such problems can be solved by using these special forms. Some more problem I give you. Suppose your integration is of the form x equal to sin inverse of x and dx. The integration of x sin inverse of x dx. In such problem, we need these special forms. Okay. Here once again you can assume, or you can use the islet form. This your islet is what? Islet. So, inverse function you can take as the first function. So, it will be your first function and here it will be your second function. So, first function integration of this is equals to integrating by parts, that means first function, that is sin inverse of x, integration of x and dx minus integration derivative of sin inverse of x, derivative of sin inverse of x, and then integration of x and dx is closed here. So, this is what? This is x square by 2 sin inverse of x minus integration and derivative of this now is what? 1 upon root under 1 minus x square, and here you can put, that is x square by 2 dx. Now, this is equals to x square by 2 sin inverse of x, and this 1 by 2 you can take out of this integration sign, and we have x square by under root of 1 minus x square and dx. This is somewhat the same thing only we have proved in the earlier case. So, you need make some adjustment here, that means you have to add plus 1 and minus 1. So, if you add plus 1 and minus 1 here, so that this is equal to x square by 2 sin inverse of x minus 1 by 2, and I put some x square plus 1 minus 1 upon root under 1 minus x square and dx. So, x square by 2 sin inverse of x minus, here what we have? 1 minus x square. So, I take this minus from here, I take this minus sign 1 by 2 upon minus, that is 1 minus x square, and from this minus 1 and x square I have taken together and taken the minus sign common. So, 1 minus x square and plus 1. So, this is equals to under root of 1 minus x square and dx. So, therefore, you can make your adjustment like this, that is x square by 2 and sin inverse of x, and this plus 1 by 2, that is integration of 1 minus x square by 1 minus x square dx, and plus dx integration of upon, that is under root of 1 minus x square. Okay. So, what we can do, this is x square by 2 sin inverse x minus 1 by 2, this minus become plus, and this minus and this plus 1, it make it minus. So, what? This is x square by 2 sin inverse of x, and this is what? 1 by 2 integration of root under 1 minus x square and minus of integration. this is under root of 1 minus x square. Now look here, this integration, this is out of that 6 special forms and its integration is known to us. Similarly, this one is what? This is exactly the same of that last 3 special forms. Okay. So, we can use special forms over here and here. This is known now to you. So, this way you can apply the special 3 forms x square root under x square plus a square root under a square minus x square as well the root under x square plus a square. Likewise, you can apply these 3 forms over these integrations. Integration by parts, integration by substitutions, all methods may require the use of these special forms. With this, we have completed our indefinite integrations. Dear students, I hope you will practice well and you can only practice, then only you can score good marks. Without practice, no one become a master on this topic. So, now let us proceed to the next topic, that is our definite integration. So, in the definite integration we use limits. The notation of the definite integration is somewhat like integration from a to b, we read it as from a to b. This one is your lower limit and this one is your upper limit. So, integration from a to b f of x dx, this is the notation of the definite integration. This one is your lower limit, this one is your upper limit. So, by name definite integration, by name it is very much clear that you will get a definite value. So, that definite value we can obtain by integrating this f of x, this integrand. Okay. So, this one based upon 2 fundamental theorem of integration, and that 2 theorem is known as first fundamental theorem of integral calculus and second fundamental theorem of integral calculus. We discuss one by one of them. Before that, what does this mean? Geometrically, if we represent this one, then what we can find? We can find the area under the curve. Let us explain. Suppose this one, this f of x is some of curve like this. This one you can define at f of x. Now, this one, let us assume this is bounded by these 2 lines, that is x equal to a and this one is x equal to b over this x axis. Now, integration of a to b, from integration from a to b f of x dx means the area, this area we are talking about, that means area under this curve, area under this curve as well under this curve bounded by the ordinates of x equal to a and x equal to b and the x axis and the x axis. So, that means if we find geometrically the meaning of integration a to b f of x dx, then we can find the area under the curve and that curve must be bounded by the a and b, that means within the interval. Here f x is, this x is lying between this a and b, this point is your a and this point is your b. So, that means you can find the area by using integration. So, we discuss this matter in our next lesson, and that your first fundamental theorem also depend upon this area only. So, what does this first fundamental theorem of integral calculus says? Suppose f of x, suppose f of x is a function defined between a less than x less than b, that means x is lying between a and b, and a of x is an some area function. Then the area function f of x, a of x is given by integration of a to b f of x dx. Then this a dash of x is equals to f of x and dx. So, this is the first fundamental. This is the first fundamental theorem of integral calculus. Now, we talk about the second fundamental theorem of integral calculus. Second fundamental theorem says, if integration of a to b f of x dx will be given by some phi of b minus some phi of a. What is about phi? Phi is nothing but the antiderivative of this f of x, integration of f of x, antiderivatives. So, that means your second fundamental theorem says that if the integration of f x over a to b can be given by, that is phi of b minus phi of, that is upper limit over the antiderivative minus the lower limit over the antiderivative. So, this is the second fundamental theorem and that we use in this lesson itself. Okay. So, here this phi is the antiderivative of what? Antiderivative of this integration. Okay. Now, what is our next? Here after doing integration, we need not to use our constant c. Why? Because we get one c here and minus of another c, and that c will cancelled out. So, here we need not use any c or any constant, and we also can write that phi of x over this upper limit and the lower limit like this. This procedure we will follow, and this second fundamental theorem we can apply now in some problems, and the first fundamental theorem that we apply in the next lesson to find the area under the curve. Now, look at this problem, integration from 0 to pi by 2 cos power 4x dx. So, what we do, that is integration of 0 to pi by 2 cos power 4x can be written as cos square x the whole square of dx. Now, this is equal to 0 to pi by 2, that is cos square x can be written as 1 plus cos 2x divided by 2 the whole square and dx. Then that is equal to integration of 0 to pi by 2, that is a plus b the whole square form, a plus b, that is a square plus 2 times of cos 2x plus cos square 2x full divided by 4 dx. Now, this 4 we can take out of integration sign, that is 0 to pi by 2 integration of, that is 1 plus 2 cos 2x plus cos square 2x and dx. Now, again, so this is 0 to pi by 2, 1 plus 2 cos 2x, again cos square 2x can be written as 1 plus cos square 2x, that is cos 4x divided by 2 dx. So, now this is 1 by 4 integration of 0 to pi by 2, that is 2 plus 4 cos 2x plus 1 plus cos 4x full divided by, that is 2, and dx is here. So, this can be written as 1 by 8 integration of 0 to pi by 2, that is 1 plus 2, that is 3, 3 plus 4 cos 2x plus cos 4x and dx. Now, it is of integrable form. We can do the integration over here. So, our integration now become so 1 by 8, that is integration of 3, that means we get 3x, that is 4 plus cos integration of cos 2x, that is sin 2x by 2 plus sin 4x by 4, and your limit is what? Your limit is 0 to pi by 2, apply limit here. From here we make the difference of definite integration. Now, we have to apply the definite integration limits. Before that, up to this point, there is no change of finding the integration of indefinite integration as well as the definite integration. Some 1 or 2 steps will more due to this definite integration. Now, we apply the limit over here this. So, what we can do? First you apply the upper limit, second you apply the lower limit. So, you are up 1 upon 8, that is equal to 3 you keep here, and this x, that is pi by 2 minus 0, okay, fine, that is 4 by 2, that is 2, sin pi by 2, that is pi by 2 is sin pi, your sin pi will be here, I keep bracket here, that is sin pi, and that is minus sin 0, and finally you keep do the, that is sin 2 pi minus sin 0, I keep within the bracket. So, now it is what? 1 by 8, here it will be your 3 pi by 2 from here, okay, and what you get from here, that is 2 times of sin pi 0 minus 0, sin 2 pi 0 minus 0. So, everything will 0 here, this term will 0, this term will 0. So, you will remain with this one only. So, that is your final answer will be, that is 3 pi by 16. This is the value of this integration. Okay. Here, look here, we apply the limit, otherwise rest of the parts, first we make the simplification and did the integrations by using the same rule. Okay. So, now here we apply the limit and we get the result, that is 3 pi by the definite value of definite integrations, that is the difference. Okay, dear students, I think you are very much clear with this one. When we use the substitution method of this definite integration, that must be one important point that to be taken care. That is what? While substituting the limit, that limit will also change. Suppose you are suppose I am giving you here a simple example. Now, look at this problem. We have to perform the definite integration of this function, that is root x upon 30 minus x power 3 by 2 the whole square dx. What do you do? That is, we can apply the substitution, that means you can assume this is as t. So, let t equal to 30 minus x power 3 by 2. Your dt will be what? Your dt will be minus 3 by 2 x power, that is 1 by 2, that means minus 3 by 2 root x and dx. So, that means this one root x dx we can write it as 2 by 3 minus dt equal to root x dx. That means root x dx can be replaced by this one. So, in the numerator we have this we have root 2 by 3 dt, and in the denominator you have this full as t, that means t square. So, what you have, I equal to integration of, that is minus 2 by 3 dt by your t. This is over that this part. So, what about this limit? Whether this limit will, there will same limit, the 4 and 9, the lower limit is 4 and the upper limit is 9? Exactly not. This limit is for the variable x, but here we are changing the variable to t, that means your limit also change. So, here when x equals to 4, x equals to 4 means you put here. So, t is what? T is equal to 30 minus, that is 4 power 3 by 2, that is equal to 30 minus 2 3 by 2, that is 2 to cancel, that is 30 minus, that is 8 and 22. So, that means your x will, that is lower limit will change to 22. So, you put here 22, the lower limit. Now, and the when x equal to your 9. So, t is what? 30 minus 9 whole power 3 by 2. So, that means this is equal to 30 minus 3 the whole square power 3 by 2, that is 2 to cancel. So, 3 power 3, that means 27, 30 minus 27, that will be 3. So, your upper limit is 3. Now, you have to perform the integration and substitute the upper limit and lower limit. So, this way you can solve the problems of definite integration by substitution. In substitution you must change the limit, otherwise your total procedure will be wrong. Okay, dear students, I think you have clear with these definite integrations. In the next class we do some problems and also see the properties of definite integration. Thank you. Have a nice day.